Rankine cycle, another important cycle in thermodynamics. And for the Rankine cycle, so the general working principle I will show with the model one here. We have a model cycle, and this model cycle here, that is from our mechanical engineering labs, and this one is actually the very simple one. Okay, very simple one, but in reality we have the additional components. But for this simple one, let's understand what happens inside the Rankine cycle. So first we have that boiler here. You have the boiler, and you have this chimney here. Okay, and then from that boiler here you get the steam. That the steam is superheated steam. If it is not superheated, you have the additional electric source here that it can get its superheated state. And then from that boiler leaves and goes to that way, and from that to the next one. And the next one will be this turbine here. So here you have the turbine. Okay, and here the blades of the turbine rotate and you can get the electricity. And after leaving that turbine, the steam comes into this condenser here. You can see the condenser tubes here. And in these condenser tubes, the steam becomes water or liquid state, and then it goes from that condenser back to the tank here. You have the feed water tank. And that feed water tank is, that pumped. You can see the pump here. It is transferred from this feed water tank to the boiler again, and the cycle continues. And we need the pump because that if you don't have the pump, the pressures at the condenser and at the boiler are different, so it cannot operate, because the boiler operates at, let's say, that P1, but this feed water tank has a pressure of P2, and therefore you need a pump to increase the pressure from P2 to P1. This is the simple Rankine cycle, and here you have the measuring sections, and you can measure the temperature and the pressure and the volume flow rate, etc. And the real Rankine cycle for the electricity generation looks something like this one. And this is the chimney here, and that chimney is at this height here, and 320 meters. And this one is Azerbaijan power plant. It is name of it. It's 24 megawatts. This Azerbaijan power plant has 8 units. You can see the units here. So you have 1 unit, and the second one, and the third, 5, 4, 5, 6, 7, and 8. There are 8 units here, and each unit, so you will have that 300 megawatts. This one, 300 megawatts. These are all separate independent units, and each of them you have this system here: the boiler, the tank, and then the turbine and the condenser, each of it. And for the condenser part, the cooling part, it uses the channel here. You can see the channel, and they are using the channel water to cool the steam outlet. And the real turbine looks something like this one. You can see it is very large, and this one, this part of the turbine is that this is the shaft of the turbine. It's the shaft of the turbine, and you can see the smaller part is the high pressure turbine, and the larger part is that low pressure turbine. And the shaft here, it is connected to the generator, and from that generator you get the electricity. And this turbine shaft and the generator shaft are on the same axis. Okay, and this one is very large. Actually, in reality it's very large, but in the lab model you can see it is very small. And this is a bit more information about the Azerbaijan power plant here. And it is subcritical power plant. It uses the temperature and the pressure that are operating in this power plant are less than the critical values of water, and it uses that fuel oil and as well as the natural gas. And these are the companies that are providing the turbines for this power plant. Okay, now that the real Rankine cycle, I have the pictures from Learn Engineering. You can get those pictures from that website. And here, this one shows the real Rankine cycle, and here you have again, these are the chimneys here. And then let's start one by one. This one is the boiler here. This is boiler, and then from that boiler, that steam comes into this turbine here, you have the turbine, these are the turbines, and then from that turbine you have the generator here, you get the electricity, and then back to these are that filters. You can see that these are filtering the dangerous gases from the fluid gases, okay? Because when you are burning the coke, or that when you are burning this natural gas or fuel oil, you have these dangerous gases that are leaving this combustion process. And here we have this filter system, precipitator, collector system, etc. And that is filtering the gases, and the dangerous ones are not, that we have to be sure that we are not polluting the environment. The pollution will be there, but we are trying to minimize it as much as possible. And these chimneys, you can see they are very high, and since you can look at here, you can see that this one is very high, because that at this height you have high velocity of the wind, and therefore that these gases cannot that collect underground here. Okay? And you are providing with a maximum height so that they can raise under the effect of the buoyant force. Okay? And so this is the main reason, and that for these chimneys, the main reason is that this sulfur dioxide gas. This one is very dangerous. Okay? Therefore, and that the filters are that collecting this sulfur dioxide gas, but it is not so effective. Some part of it leaves the system, as well as the fluid gases leave the system, and therefore you have this chimney that is used at a very large height, so that there is no any pollutant gases collecting under these places here, because here if they are collected it will be dangerous for the environment. Okay, but the bad side and the drawback of this Rankine cycle is that this sulfur dioxide creates acid rain, and therefore that however you try to minimize the pollution, that you will not that get rid of it. You will always have this pollution from these power plants, even this one or the others. Okay, and then you have the generator here, and we have these cooling towers here. And we have 4 cooling towers, and we will see next slide why do we use the cooling tower. And you can see that these are the outlets of the turbine, and here you have the condenser, and this one is the condenser that we are using. If you think the condenser as a heat exchanger here, this one is the condenser that I am drawing, and in one side you will have that steam from the turbine, and that steam will leave the condenser, and this steam is T-hot, and at the exit it is cold at cold temperature. Since this is a heat exchanger, we need also the cold fluid that enters our system, and that cold fluid, so T cold in and T cold out. This one is another circulating water here, and this one is the circulating water for our Rankine cycle. This cold water is supplied, you can see the condenser here, so a hot water and the cold water comes into the system to cool the turbine outlet, and it leaves as hot water to the cooling tower here. At this cooling tower, so what we have is that when the hot water out of the Rankine cycle comes into contact with the air, here you have the air, and this air is cold, and the water here it is hot. Okay. It gives its energy to the air, but some of the water it leaves the system. Okay, the steam, some of the steam it leaves the system, and that when that steam leaves, you will have that the currents that are moving out of this cooling tower, and that current will also as a result affect the air here, and the air will start to move upwards. Okay, and by this way you will create a natural draft. Okay, or you can say that natural convection. You will create a natural convection or natural draft of the air by this movement of the steam. And then that water will become, you can see that here it is in this form of a spray. Okay, because by using sprays you are increasing the surface area of the water so that you have better heat exchange process, because heat is proportional to the surface area. Okay, and then we have that different thermal power plants, and all of them are working with the Rankine cycle. All of them are in the form of the Rankine cycle, and for all of these thermal power plants you have different, that heat source. So heat sources are different. In one case we can use this fossil fuel here, so that fossil fuel before entering, so that this fossil fuel you are burning it. As a result of this combustion you are heating the turbine, so you are heating the water here. That water enters this turbine as a superheated steam, and you get the generator power here, and then it goes to the condenser, and then from that condenser to pump, and then you are recirculating the water here. And on this side here you have that some processes before entering the boiler here, before burning it. For example, you have the storage process and processing, like crushing of the coal, pulverization of the coal, etc. You have these processes before burning the coal. You are pulverizing the coal to make it, to have that, when you pulverize it, it has higher surface area, and higher surface area for the coal means that you will have better burning combustion process. Okay, you have the combustion here, and when combustion happens you are heating the water here, and then you have the outlet for that combusted products, and here you have also some processing, like you are using that selective catalytic reduction for the nitrogen oxide, and also a precipitator for ashes, and the scrubber and absorber system for sulfur dioxide. Okay. And if this system is not enough, and at the end you have this chimney here, and then the rest of the combusted products leave from this system. Okay, for the boiler system you are using fossil fuel for heating the water, and for cooling the condenser here, that condenser water from the steam outlet, the turbine outlet, to cool it we are using the cooling towers. Okay, and in that cooling tower, that cold water is pumped by this pump here into that system, and then when it leaves that system it becomes hot, and then it comes again to this cooling tower in form of the sprays, and then it becomes that water here again. And you can see that here we have that 3 cycles. If I show with the arrows here, it moves in that way, moves in that way. Similarly for this part you have that direction. Okay, so here you have that 3 cycles, and the first loop is here. This one is the first loop, and you have the second loop here, and you have that third loop here. You can see with the colors here. Okay, and also one more thing here is that the cooling towers are in the form of the hyperboloid. Okay, this one is for the structure of the cooling towers. It gives the better strength, and also better natural draft inside the system. Okay, what else do I have to talk about? This one is that, and this one is the chimney, you know it, so we'll talk about this one. And that's all. And another method to heat the water inside the boiler is that we can use renewable energy. So we can use these collectors here. Okay. And what we have is that when the sun energy falls on these concentrators here, this one is not collector, sorry, this is concentrator. So we are using the concentrators here. Okay. And when the sun energy falls onto that concentrator here, and that falls, and when it falls on it, you can see the tube here, and these tubes are on the focal length for the sun rays, and when it reflected back, it heats these water tubes, and here again, and here again, all of them are heating these water tubes. You have also another array here, you have another array at the back, and at the end you are getting this hot water. And if you show this one in a figure like this one, you have n number of concentrators, And for that n number of concentrators, you have that outlet here. Okay, this one is the outlet. Okay, even you can use some pump inside the system, or to eliminate the pressure losses. And from that outlet, it becomes very hot here. And inside this boiler, this is again the boiler. You are having heat exchange from the outlet of the concentrators and with this boiler system here, and then it goes to that pump, and then again back to the concentrators here, and then circulates back. You can see that the only difference is that here we are not using the fossil fuel, but you are using the energy of the sun. The rest of the system is the same. Or it may be that we are using the geothermal power, geothermal energy. Here you have the pump again, and inside the under the earth, here you have that in some places you have hot water. Okay, so you can use that hot water to generate electricity. So similar to this one, we are using the geothermal energy, and from that geothermal energy you get the hot water, and then by using the pump it goes again back to the boiler, and you are transferring back to the earth. And here again you have that heat transfer process from that within that boiler here, and you are getting again electricity in the similar manner to this one. Okay. One more is that this one is from the book by Shapiro, and here we are using that nuclear power plant. You can see that the process again is the same process. You have the boiler here, and the boiler is given. You have the turbine and the condenser, pump, cooling tower, etc. But the only difference is that you are using now nuclear energy, and inside that nuclear containment you have one more loop here. So you can see on all of these systems you have that 3 loops. You have that first loop here, you have that second cycle here, and you have that third cycle here. And here you have that rods, and from this rods you have that nuclear reaction, and then you are heating the water inside the system, and it is pumped and then back to the system, and then circulates here. It will have high energy, and that high energy gives its heat to the boiler of the Rankine cycle. And then you have that electricity again. And one thing I have forgotten to say is that the makeup water. And if you remember, we have said that for the cooling towers, some of the steam leaves the system. You can see that the steam here, and some of steam leaves. Therefore, what you have to do is that you have to supply some additional water to accommodate that loss of water. That additional water that's supplied to the system is called makeup water, because some of the water is lost, as in the case of the steam. Because during that process, that heat exchange process, you have the mass transfer with the air, so it exchanges heat with the air, heat as well as the mass. The humidity of air, and if it is inlet, you have the air, and there are inlets for the air. There comes in that way. At the beginning, let's say that humidity of air is 0, but at outlet humidity of air is 90%. This one is humidity. That humidity ratio increases with the amount of the water. So by this way, you are losing that mass of water. But to accommodate that mass of water, you have to supply some makeup water into the system. What comes to analysis of the simple Rankine cycle here. So for the simple Rankine cycle, this one is the ideal one. We have the turbine, and we have the boiler. This one is actually pump. We have the pump here. You have the boiler, you have the turbine, and you have this condenser here. And this is the cycle. And if you remember from the second law of thermodynamics, That second law of thermodynamics says that if you have a heat engine, in this case heat engine is Rankine cycle. This Rankine cycle gives you electricity, which is work net out, and you are providing some heat from the boiler. And you should know that for the Kelvin-Planck statement, you have to give heat out of the system. Okay, so that condenser is always required. Okay, it is due to only the second law of the thermodynamics, or Kelvin-Planck statement. Okay, this is the process for the ideal and the simple Rankine cycle. So the ideal means that here we have that pump, which is reversible and adiabatic, and the turbine is again reversible and adiabatic. Boiler is isobaric, you don't have any pressure drop in boiler, and the condenser is also isobaric, you don't have any drop in pressure in the condenser. These are the components. Now let's analyze and put some numbers here. This one is 0.1, this one is 0.2, and the 0.3 and 0.4. So from 4 to 1, pressure is the same. P4 is same as P1. This is the first thing. And the second thing is that for the pump, it always works with water, with liquid. So here you should always have the liquid state. So the minimum is that if you have the minimum case, that x should be 0 for the minimum case. For other case, it can be that compressed state too. Okay. But the minimum case is that it should be with x is 0. And then from 2 and 3, you have also the same pressure, which is P2 is the same as P3. Okay. And from 3 and 4, you have that difference of the pressure. Now that P4 is less than P3 because turbine uses energy. Okay. Now what you notice is that P4 is same as P1 and the P2 is same as P3. So with this manner, you have two isobaric lines. So two isobaric lines, two pressure lines. One is the maximum and the other one is the minimum. And for maximum pressure, Pmax is that before the turbine, which is P3 and the P2, P3 or P2 because they are equal, and the minimum pressure is P1 or P4. This is the minimum pressure. And now we are going to show the cycle in TS diagram, and you have to know that TS diagram is the most important one for the thermodynamic cycles. Now I will start from the first state, this one. And in most of the thermodynamic analysis for the cycles, that start point of the pump is taken as x is 0, okay, mostly. You are taking the start as that inlet for the pump as the x is 0. Okay, now I'm going to show the values on TS diagram, but before showing it, let me start with that modifications to Rankine cycle. So first thing is the simple ideal one. Okay, this one is the start point, and this one is the simple and ideal one. All of them are the simple ideal one, but this is the start. We start with these values, which you have that 75 kilopascals and the 3 megapascal of the maximum pressure. You have that this one is the minimum, this one is the maximum, and the third one is this one is lowest isobaric line, highest isobaric line, and this is the peak temperature. Now I will show it. First one, and then the next ones are the modifications. I will talk about it later. Now let's start from the first one. You have the maximum pressure, which is 3 megapascals, and the minimum pressure is 75 kilopascal. Now you can see the values here, that P4 is 75 kilopascal and the P2 is at 3 megapascal. So this line is P2, you can see that P2 line here, and you have also that P4 line here. Okay. Now let's show. I will start from the point 1, and the point 1 we have said most of the time we take the quality as 0. So P4 and quality 0 is here. And this one is reversible and adiabatic. Therefore, when you move from 1 to 2, you will go in isentropic manner. Entropy is constant, but the pressure will increase. That pressure increase will be from 75 kilopascal to 3 megapascal. And that one is this pressure line here. You see that pressure line? Okay. This will be the work of the pump. This one is 1, and this point here is 2. Okay. Now next process comes, and that next process is that this one is the boiler. And in boiler, pressure is constant. You move from 2 and 3, but in the boiler, it is also given that this is the peak temperature. I should first select the peak temperature here. This is the 350. It should be at outlet. So this one is that outlet of the boiler, and therefore I go in that way. And I should have that 3 megapascal with this temperature. I should go that way. So boiler starts from that one. It increases the temperature. You can say temperature increases. You have the boiling process, phase change, and then you are heating the superheated vapor. This is the 3. And then from the 3 to 4, you have the turbine where entropy is constant, and you will go in the vertical direction. So I will have something like this. Feel the initial pressure, which is that 10 kilopascals, 75 kilopascals. Now let me write it. This will be the point 4. And if I combine it, okay, we will have this process from 1 to 2, and it will pump, and from 2 and 3 you will have the boiler, from 3 to 4 you will have the turbine, and from 4 to 1 you will have the condenser. Okay, and the values are given. You have the 75 kilopascal and the 3 megapascal values, and the temperature is that 350 degrees Celsius. And what you can do is that you can find the efficiency of the cycle, you can find the quality, moisture content, and the work of the pump, heat input and heat output, as well as the work of the turbine. Now let's solve it. Let me start with the state 1 here. For the state 1, I will just take the HF values from the 75 kilopascal. You go to 75 kilopascal, and the HF value will be just 384.44 kilojoules per kilogram. And since the enthalpy is the most important property, I will not work out the other ones, but if you are interested, you can get it. Now comes the state 2, and for the state 2, S2 is same as S1. And S1 is SF, and it is given in the question that it is 1.2132. It is the kilojoules by kilogram degree Celsius. And this one, if you check the 3 megapascal value here, for 3 megapascal, that F value is 2.64. Therefore, this one is the compressed state. And if you go back to chart here, you can see it is also the compressed. But for compressed state, for this pressure value, no table. And this is the problem with the compressed tables. So better option is that, so what you will do is that you will find the first law for the pump. If you write the first law for the pump, you will see that it will be simple. So that it is 1 and it is 2, and you have that work in for the pump. So enthalpy in plus work in of the pump will be equal to enthalpy out. And the work in of the pump, so from the thermodynamics, fluid mechanics, if you remember, it will be that delta V by rho plus that V squared by 2 and plus GZ. This one is delta. All of them are delta. Let me correct it so that it will be kinetic energy change plus potential energy change. For the thermodynamic problems, we don't consider this one, and it will be just delta P by rho. Delta P by rho, which is same as nu into delta P. And therefore, that nu delta P plus H1 will be same as H2. H1 value is okay, I know it. And nu value, I will take, since it is incompressible, it doesn't matter which state I take. I will take the state 1 as the nu value, and the nu value will be that 0.001307. Okay, it's 0.37. And the delta P value will be that 3000 kilopascal minus 75 kilopascal, the difference in pressure, multiplied with 10 to the power of 3. And if you add that one with this nu into delta P value, you will get enthalpy at state 2. And the enthalpy at state 2, if you calculate it, you will get 387.5 kilojoules per kilogram. This is for state 2. Now comes the state 3. For this one, I know the temperature, I know the pressure. So I will go to the saturated region firstly, and I know that this temperature is lower than that one, 350. It means that it is superheated. Even if we check it from the chart here, it is superheated. For the superheated values, we'll go to superheated region, 3 megapascal. First one is nu, the second one is U, and then enthalpy, and then entropy. And the 350 degrees, the enthalpy value is this one. It will be that 3116.1 kilojoules per kilogram. Now comes the last state, which is 75 kilopascal, and the S4 is same as S3. Therefore, I need the S3 value here, which is the last one, and it will be that 6.7450. And the S4 is same as S3. I know the pressure, so I got the pressure here, and I know SF, I know SFG, and I know SG. So therefore, I can find the quality here. So that quality will be equal to that. So just let me write the formula. So you will have that S4 will be equal to SF plus X into SFG. And SF value is equal to, for 75 kilopascal, it is at 1.2132. And SFG value is given as 6.2426. And the S4 value is given as 6.7450. Okay, from here you can find the quality of it, and the quality value will be 88.6%. That is the quality. And if I know the quality, now I can find the enthalpy at state 4. It will be that enthalpy F plus that X into enthalpy HFG. And the enthalpy F is for that 75 kilopascal. This one is the enthalpy F. Enthalpy FG is this one, and the quality is that one. If you do that calculation for the state 4, you will find that enthalpy at state 4 will be equal to 2004. I have found all of the enthalpy values. Now the next is that I know the work of the turbine, the work of the pump. The pump work is that we have set it nu into delta P, and when you calculate it, you will get the pump work as 3.032 kilojoules per kilogram. You can see it is very small value. The resonance due to small amount of this specific volume. And the work of the turbine will be, if you go to the graph here, and it will be that H3 minus H4. And that value will be 712.7 kilojoules per kilogram. And then the Q by condenser, and this one is the Q out, heat transfer from the system to the environment. It will be that H4 minus H1. Calculate it, you will get that Q out by the condenser is 2018.6 kilojoules per kilogram. And then Q boiler in heat transfer will be that H3 minus H2, so that you will have that Q in value will be equal to 2727 kilojoules per kilogram. Okay, these are the heat transfer values, and you can find the efficiency of the cycle, and the efficiency of the cycle will be that work net out and divide by Q in, and this one will be equal to that. So work of turbine minus work of compressor divided by Q in, and the result is 0.2602 or 26.02%. That is the efficiency of the cycle. Or if you can write this one as that eta will be equal to 1 minus Q out by Q in, and you will get a similar result. Okay, if you go back to the chart here, you can see the efficiency is the same efficiency that we have got, and the quality also, the moisture content, which is 1 minus X, it will be the same here. Work of the pump and the heat input, heat output, all of them are the same. Okay, that we have found here, and the quality is here. You only have quality at 0.4. Now we will do one modification for it, and the rest will be for the next lectures. The first one modification will be that. So let me first write the formula. So let's see, you can see that what is the reason of the modification. So that eta will be equal to 1 minus Q out by Q in, and that is the formula for the eta. And the one part means that you have the 100% efficiency, and therefore this part Q out by Q in should be small. And to make it small, that we know that this Q out is proportional to outlet temperature, and this Q in is proportional to inlet temperature. Or if you go back to here, that temperature at outlet is at temperature at inlet, sorry. So you should make that T in, T3 as high as possible to get more energy, and you have to give this T1 as low as possible to get, sorry, T4 here. At T4, you have to get the T4 as low as possible to get more power. So this one should be low, and this one should be that high. Okay, if you supply these ones, you'll get higher efficiency. Now let's see what they have done in the first part. You can decrease the pressure. Let's see if we decrease the pressure, what happens. So that pressure decreases, the rest of the values is the same, 3 megapascal and 350 degrees Celsius. If you do that, the pressure drops from that 75 kilopascal to 10 kilopascal. Wait, 10 kilopascal line is this one. The pump, the turbine, the peak temperature doesn't change, only you are moving the line here. Therefore, the pump will supply the energy from 1 prime to this position here, this 2 prime. And it's not 2 prime, it's the same pressure line. You have the same pressure line here. This is 2 prime, and you will have that curve. Peak temperature doesn't change, it is the same, and you will have that line doesn't change, only you're moving now here, which is 4 prime, and then cycle goes in that manner. Direction, of course, is in that way. Okay, so you have the 1 prime and you have the 4 prime, and you have this relationship. Now you can see that the temperature has dropped to this value. At the beginning it was this amount, now the temperature has dropped. Q out dropped. We have got one advantage, that so by dropping P minimum, you have dropped that T out, it dropped. It is okay, we have got our advantage. This is the advantage. Now let's see that disadvantage. The first disadvantage is that if you look at the chart, you can see 4' has more quality, has less quality than the 4. The less quality means that more moisture content. So less quality means that more moisture, and more moisture means that it is dangerous for the steam turbine. Okay, that because it can create erosion on the blades of the steam turbine. Therefore, this is not desired. And the second disadvantage is that, let's go back to the chart here. You can see that now at the beginning case, the boiler was, that heating from, let me show it to you. So at the first case, boiler was heating from that one to this one. Not it heats from this amount, which is 2'. You can see the boiler heats additional amount of the heat transfer to the fluid. So now the boiler heat input should increase. Boiler key increases because at the beginning it was from 2 to 3. Now it is from 2' to 3. 2' has lower temperature than the 2. Okay, these are the disadvantages. Now let's see the chart if it is consistent. The first thing is that the efficiency increases. Yes, it is good. Efficiency increases because you have dropped the T out. Okay, this is the, let me write it. T out drops by that P minimum drops. But the quality, you can see that quality has increased. Sorry, this is not good. Therefore, moisture content increased. Work of the pump, it is approximately the same. And the heat input, you can see it increased. And the heat output, this one dropped because T output dropped. And then the work of the turbine has increased. It is also good. It also affected our system because that heat output dropped. Therefore, that work of the efficiency increased. But this one is related to efficiency. There you can see the advantage that we have created by dropping the outlet, so by dropping the turbine pressure. Now we'll look for the rest of the cases and see how it will affect the efficiency in our next slides. So I'll stop the recording here.